Are you running for a while?
Yeah, mine's up 2 hours. Well, I haven't got a whole lot.
So you did that's the one part.
The first part,
Or are you going out reading? Confusing. Yeah. What is this the margin?
What's up, dudes? Let me see your SVM, dude. Let me see it. 98, that's quite good.
What did you get?
That's not that much better, but it's 3% is a lot when you're that high.
No,
Well, there's a 3% difference between ours. I'm saying when you're that high
they're
already.
89 though, not 98.
Oh. You remember for some reason. Okay, man. Yeah, you're murdering it.
But I have 100. The only way I can get that is AC. These are what's going to come. This is a whole the same no matter what and regularization is like finding regularization if I change it. It's like the first one, first default. It's always
What does your SVM look like?
so.
Oh, you're not adjusting your bias at all, huh? Or just the bias in your weight vector? So that's probably the difference. I was wondering, I think we're supposed to think, because the bias is supposed to be like baked into your weight vector, right? In all these examples, so I think, that's what I was trying to figure out the other day too. So I think essentially, I can't decide if you, I think you,
We'll go back and talk about that.
yeah, that's all it tells you that, well, maybe that's right.
Remember to talk about
Have you done the SVM yet, Ken?
Yeah, I haven't started yet. I was just reading this line and figure it out.
Yeah.
Like that. This is all this. This is the same size system.
Yeah, they're the same thing pretty much. So I guess what I'm thinking is every time you do update, your bias is supposed to essentially on the end, your void vector is just one more entry, or your bias is one more entry in the vector, right? So essentially you'd be multiplying your bias by that and then adding. Actually, no, you'd just be multiplying it by that because this is one dimensional less than. So you'd just be multiplying by that, multiplying by that. So he says that, he said a while back, he's like, I'm not gonna like write out that I'm using a bias anymore, but the bias is probably more heavy. So like, yeah, you have one more entry at the end. That's one extra. Actually, I think I did. I think I did that If you want to bias, essentially, it can be
Okay, class, we should start. Have a somewhat packed schedule for the rest of the semester now. We'll see how much we can get through. So there is a homework that's due this Thursday. I'm guessing most of you have started by now, and I know there are many issues with implementation, in particular with scalability of your code. And the main thing is, so it seems like there are two kinds of problems that people are facing. One of them is that decision trees take forever to train because the number of features is large. And the second problem is that so there was some issue with even the SVM, other algorithms also being slow. The second one is easier to fix. And already many of you arrived at the solution. And the answer is use sparse arrays or sparse vector representations. There are libraries in various languages which do that for you. I personally have implemented one such thing for myself because I just, there were no libraries when I was starting off. The main intuition is we don't need to store non-zero values. So instead of storing a massive vector or an array with most of whose elements are zeros, you only need to store those entries whose the indices of those features that are non-zero. In particular, in this specific data set, there's another optimization that you can make. Notice that all the features are either 0 or 1. So you don't even need to store the 1. All you need to do is store a set of indices of the non-zero features for each example. That's not true for the weight vector. The weight vector can be has to be an array or something more, some sort of a dense representation. So this can give you a pretty big speed up, and that should take care of all the SVM and logistic regression kind of issues. And I suspect some of you have already arrived at this essentially this intuition, or have used a library which has made this disappear. Is that right? With regard to SVM and logistic regression, are there scalability issues? I'm assuming no. Okay, then comes decision trees. As I mentioned in the class last week, actually, training decision trees in this data set is going to be slow. So we thought we could help you out by asking you to train trees only of depth 3. How's that working out? 1,000 trees of depth 3? Is that faster? Is that hours, days? Hours. On the bright side though, you need to do it exactly once. Because you need to do that once when you train bagging. Store those trees, and those are the trees that you'll use for the next two questions as well, for the logistic regression on top of trees or SVM on top of trees. So you need to train 1,000 trees once, and thankfully there is no cross-validation needed for bagging. All you have to do is just sample examples and train trees. It's a one-time operation, so I'm not super worried about it. The only problem will be when the TAs have to run your code. Because every homework is going to take a few hours to run, so we're going to evaluate your code on a different data set. Just that part alone to make sure that everything is fine. There are no real tricks with respect to that bit. In the worst case, and absolutely the worst case, if nothing works, then if you can't get a decision tree of depth 3 even, so try depth 2, see if it works. And mention in your write-up that this is what happened, and give some estimate of the time that it takes. Any questions? Yes?
So each decision tree is like 15-20 minutes, and like 1,000 is...
So each tree takes 15 minutes?
Yeah.
You might have to rework your code a bit. You might have to profile your code. And when it comes to profiling code, I would say work in a group or multiple people. I don't mind if you kind of share tips on Canvas. When I trained 1,000 trees of depth 3 on rather hastily written code, it took me about a minute.
Just picture.
So you might want to, what you should probably do is profile your code and see where it fails. If a single tree of depth 3, I keep saying tree of 3 and that's very difficult to say. If a single tree takes 15 minutes, there are clearly opportunities for you to, there must be opportunities for you to make it faster. Look for things that are, it's possible that you might have the opportunity to cache some computation. You might be using data structures that are O of n rather of O of 1. And that makes a big difference. For example, just as an example, I'm not sure how your implementation is. If you're doing, sometimes, I'm not sure exactly how this shows up, but the difference could be between, say, using hash maps versus a linked list, which takes O of n to search. I don't know why you need to do that, but just as an example. And you might have to think about the data structures you're using. Feel free to ask questions on Canvas. And this is the kind of stuff that is so implementation specific that I can't give anything more than such very, very generic advice. But I don't think that should happen. If you want, we can talk about it after the class. Yes?
Any chance we could get an extension for this one, since the logistic regression material wasn't introduced till...
Yeah, so I will decide that after class today. I've been thinking about that as well. I'll let you know. Watch out for an announcement today. There might be an extension. Maybe it won't be more than a day or 2 tops, because frankly speaking, logistic regression should be easy to derive and implement anyway. So, but just keep an eye out on Canvas. Any other questions? Did you have one?
Are we going to continue with logistic regression?
Yes.
today?
Yeah. Let me just make another reminder. It's already the end of the semester. So it's kind of disappointing that the semester is ending so quickly, but that's what it is. We have a final exam, we have your projects. You should be hearing back about your projects by the end of this week. So by Friday, I'm hoping to have all the project, what do you call this, the proposals, the intermediate status reports graded. So you should be hearing back. I'm going to prioritize it by going through the exploratory projects first, because those take longer for me to actually read. For the competitive project, go ahead, keep working through. For the exploratory project, you should be hearing back something very soon. The project report, final report is due by 15th. When I say by 15th, I don't mean it is due on the 15th. We'll have the submission window open on Canvas, say, by the end of this week. You can, if you think you're done, you can submit. You don't need to let it all pile up at the end. What you need is a short report. I can't remember the number of pages. It's specified on the class website. And also submit your code, but please don't submit any data. Submit a zip version of your code on Canvas. There's going to be a final exam. It's in class on December 14th. And whether we like it or not, most likely not, it's at 8 a.m. So it's in class right here at 8 a.m. on the 14th. I'll keep reminding you, and it will cover everything from everything that we did not cover in the midterm. So from computational learning theory. And it will be the same, roughly the same kind of format as the midterm. Any questions? Yes.
Will there be like some sort of study thing posted, or?
There should be something posted.
Okay.
Alright, I'm going to continue with logistic regression, and my goal is to try to get to the end of this as soon as, kind of in a bit of a hurry, because the neural network material is rather large. Alright, just a quick reminder of what we saw about logistics. Did you have a question?
I was just wondering for reference, we don't assign that after this one.
That is part of the thing that I have to decide based on whether I give an extension or not.
How about I make a suggestion? I'd love to implement a neural network, so what if we just had a smaller size homework for the last one?
I'll think about it.
All right.
It will probably be a small, if at all there is an assignment, it will be a much smaller one. And I'm considering something like your homework 3, rather than something that you submit, something that's completely on Canvas and multiple choice and somewhat tricky.
No, I want to implement it.
Oh, you want to implement it? Okay, let's. You can implement it anyway. Nothing stops you. We can talk about it offline. And yes, you can totally implement it, and it should be fun. You can also do it for your project. Anyway, but yes, you should totally try to implement everything that you see, because and try. It's one way to break your implementation, as you might realize from this homework, is to scale your data. Things that seem to work with small data set sizes tend to break if you haven't thought it through. And also they tend to break in peculiar ways with different kinds of hypothesis classes. They break in peculiar ways with whether your data is sparse or not. Imagine the same data set, but your examples are not sparse. You have 50,000 dimensional examples, and every one of those dimensions is present. How are you going to do the dot product? I mean, everything is going to become slow. That's the kind of place where NVIDIA and other companies are really making a killing these days, because they essentially, the reason NVIDIA stock is so high today is because they have this hardware system that does dot product super fast. And so much of what we do involves the dot product. And they specifically handle dense dense dot products really well, either vector vector multiplication or matrix vector multiplications, and they do that super fast and faster than anyone else, it seems. So that's one of the reasons why they are doing a good job. But going back to away from the digression, yes, you should totally implement, and most likely what will happen is when you implement a new algorithm, you will find that some of the assumptions that you made for the previous ones don't hold up. So it's totally worth doing. Alright, let's come back to the lecture. So in the last lecture we saw, last Tuesday, we saw logistic regression, and I set it up as a classification problem. Our goal is to produce labels -1 or 1. We are given a data set, but instead of predicting just the label directly, we are going to predict the probability of the label being 1. And the logistic regression model says the probability of the label being 1 is obtained by taking the dot product of the example with a weight vector and passing it through this sigmoid function. The sigmoid function is simply 1 over 1 plus e power minus z. Sigma of z. Looks like this. And once you get a probability, prediction is easy because you can convert the probability into a label by asking if the probability is more than half. If it is, then the label is what? Okay, so this is what we saw, and we were going through the process of, and we also I also mentioned that logistic regression has interesting connections to the naive Bayes classifier. The naive Bayes classifier can be seen as a generative model for a certain posterior probability. The logistic regression classifier is a discriminative model for the same posterior probability, and they form a discriminative generative pair. And we started looking at estimation, how to train a logistic regression classifier. Notice the key thing to keep in mind is the logistic regression classifier produces a probability. So it is a probabilistic classifier. In addition, we can also use this as a way of assigning the probability of a data set. So we can do maximum likelihood estimation or maximum a posteriori estimation. And in the last lecture, I walked through this maximum likelihood estimation for logistic regressions. The setting is we are given a data set S which has pairs x, y, and our goal is to find a weight vector W such that the likelihood of the data set, the examples that we observe, is maximized. We know that all our examples are IIDs, so I answer this question. We say that the probability of S is the product over all examples equals, let's say we have m examples, product of the examples p of yi given x and w, xi and w, and this is exactly what the logistic regression model gives us. So I can replace that, and we can do the same sequence of steps that we have been doing for maximum likelihood estimation, which is convert the product into a sum by taking log likelihoods. And essentially, if you just work through the algebra, and I hope you have already done this, this product becomes equals to the sum log posterior, and substituting the posterior probability into this thing gets you this optimization problem. So the goal of maximum likelihood estimation is to find, for logistic regression, what we started off with was to find the maximum likelihood estimate of a discriminative probabilistic classifier, namely the logistic regression classifier. But it's not enough to say that it's a probabilistic classifier. We should say, we need to say it's a probabilistic classifier under what model of the label. It's a probabilistic classifier that assumes that the label probability is produced, is the logistic function, or it's the logistic model for the posterior. So our goal was to find the maximum likelihood estimate of a discriminative probabilistic classifier under the logistic model for the posterior distribution. That's what we wanted. And you just do a little bit of algebra and you get an equivalent goal is to find a weight vector W that maximizes the sum of this quantity here. The thing inside the blue box here at the bottom without the minus is the logistic loss. So essentially the goal, an equivalent goal to maximum likelihood estimate is to minimize this empirical logistic loss over the training set. We will revisit what loss minimization is in a bit, but essentially these two things are equivalent because from here to here is literally 3 steps of just simplification. So these two things are equivalent and we can solve this problem. How do we solve this problem? I'm not going to tell you, but that's what your homework is. We know how to solve this problem because it's essentially maximizing or minimizing the sum of losses. You can use stochastic gradient descent. What you have to do for that is to derive the gradient. In order to derive the gradient, you need to take the gradient of this quantity here with respect to W, and that should not be terribly hard. I'm going to put a pause on that for now and take you to the next step. We could also have done maximum a posteriori estimation. So the difference between, just to remind you, the goal of maximum a posteriori estimation is to find the hypothesis H that maximizes probability of the hypothesis given the data, which is exactly the same as maximizing probability of data given the hypothesis times the probability of the hypothesis. This is what maximum a posteriori estimation was. In maximum likelihood estimation, says probability of hypothesis is constant. And you plug that in and you just have to maximize this quantity here for maximum likelihood estimation. That's what we saw, literally just now. But in order to start thinking about maximum a posteriori estimation, we have to drop this assumption. The probability of the hypothesis is no longer a constant. We get to parameterize that. We get to say something about that. It's essentially the prior over the weight, because the hypothesis is completely the weight vector. Again, in order to come up with a prior over the weights, we need to make an assumption. We need to say something about what we believe the weights are generated from. Let's say, just to make life a little simple, let's say each element of the weight vector is an independent random variable. Every element of the weight vector is randomly drawn from a Gaussian distribution centered around 0 and some fixed standard deviation figure. What this means really is, let's kind of think about this assumption. Every weight in the weight vector, I'm assuming, is coming from a Gaussian distribution, which centered at 0, which means the most probable weight is what? 0. So essentially saying, in the absence of any information, I prefer the 0 weight vector. And there has to be some pressure from the data to pull me away from 0. And this pressure is applied independently on each element of the weight vector. That's why we can say the probability of the prior probability of the weight vector is the product over all the elements of the weight vector. This J goes from 0 to D of P of the probability mass associated with that value of the weight. And since we assume it's Gaussian, this is just a Gaussian distribution with a 0 mean. So this is the prior probability of the weight vector. Okay? And for maximum likelihood map estimation, with that assumption we get the prior probability, and now we can write down this product. let's, before I start writing the product, any questions? Yes?
If you want to move on from this, there's a gap in my understanding. So we presented logistic regression as a deterministic classifier. Discriminative, sorry.
Yes.
And my understanding from that is we go directly to learning the posterior.
Yes.
So I'm getting confused on why we're throwing in priors in my
Haha,
thoughts.
excellent question. So, and this is a confusion that should be, if you thought about it, this confusion should be there. So there is map learning and map prediction. In map learning, the goal is given data set, find hypothesis. By saying, I'm just going to write max, but there is an argmax. Max over hypothesis, probability of hypothesis given data, which is equivalent to saying max over the hypothesis, probability of data given hypothesis times probability of hypothesis. This part here is the likelihood of data given hypothesis. This is prior over the hypothesis. Right?
Mhm.
Okay? That's map learning. In map prediction, the goal is given example, predict label. Example and a hypothesis, predict the label. So we want to maximize y we have a hypothesis. Our goal is to find the label that has the highest probability for a new future example. And this is the posterior distribution of label given example and the parameters. The main difference is here we are finding a hypothesis, here we are finding the label. It just so happens that we are using the same mathematical criterion of map both for learning and for prediction. The logistic regression classifier directly models the posterior distribution. But we still can learn the logistic regression classifier in a map fashion. And if we learn it as maximum a posteriori, then we need to specify the likelihood. We have the choice of specifying a non-uniform prior if we want to do map estimation. But this prior is over the hypothesis, which is essentially saying a prior over the weight vector. And this is a confusion that is easy because we are using the same condition, except the random variables on the left and the right are different. On one side, the random variables are data set and hypothesis. On the other side, the random variables are examples and labels. For logistic regression, there is no prior because we are directly modeling the posterior. There is no prior parameters. In contrast, for naive Bayes, we have the similar map prediction would be max over y of x given y comma h, p of y given h. And we have the prior over the labels. Does that make sense? Okay, good question. This is probably important, this distinction. Or it's definitely important. It's good to understand this distinction. Okay, so for map estimation for logistic regression, we just found out that, or we just assumed that there is a prior distribution over the weights. The weights can come from a Gaussian distribution. Just to remind you, I'm going to put the maximum likelihood estimation on this side. We wanted to maximize this quantity and we ended up coming to the minimizing a loss function. I say minimizing because there's max of a negative. Let's work through this process again. to see what changes. The goal of maximum likelihood estimation is to maximize the posterior. I just told you that, so I'm not going to say that again. Our goal is to maximize, or at least I'm not going to pose it as a question, even though it's written here that way. The goal is to find the weight that maximizes the posterior distribution of the weights given the data set, which is exactly the same as, which is equivalent to maximizing the product of the likelihood term and the prior. The likelihood was what we used in the maximum likelihood. The prior is what we just came up with. What we have to do is multiply those things and try to maximize. So our goal of learning is to find a W that maximizes P of W given S. Essentially, we are asking what is the most probable weight vector under this set of assumptions. And that's the same as maximizing this product. And we know both terms of the product, but before we start putting things in, let's take log so that we can actually write these things. And the max of this, the log likelihood of the data plus the log prior. The log likelihood is exactly what we expanded out in the previous thing, right? It's what's kind of written in faded font here. So this log of this quantity is exactly this quantity here, which is in the box here. So I'm not going to work through that. All you have to do is substitute the logistic model into the likelihood term, and you'll get that this term here. Let's worry about the prior of it. Now, log prior, I already know this is the prior. Taking the log will convert this product into the summation over the log P of Wi. Now, log P of Wi has some term that does not have any Wi and an e power minus Wi term. But taking log kills out the e power, so that gives us minus Wi square divided by sigma square plus things that log of these things which are really independent of W, so I'm just going to call them constants. And one of the worst ways, as I mentioned, to see math is to see someone else doing it, and even worse is to see someone else just show math on a slide. So I'll give you a minute to digest it. And you can also think of questions along the way. Any questions? Or objections? Or if you want, you can ask me to work it out again. Or work it out.
Shouldn't that be sigma I?
No, we assume.
Doesn't each dimension have a different 70?
No, I assume that all the weights come from the same. All weights are drawn from the same Gaussian. Independently. So it is not sigma I. And sigma is a constant. I'm assuming that sigma is a constant. Sigma does not change, which is why we're not going to learn it. It's a Gaussian that we know.
It's not a hyperparameter.
It is a hyperparameter. Yes. If sigma is really, really small, that means that. So let's consider two options. What happens if sigma is really small? What are we saying about the nature of this Gaussian? Is it very wide or is it very narrow? It's very narrow. If sigma is really small, what we are saying is, I don't like it if my weights have to go too far away from the origin. Because the prior, this term here, forces weights to be close to the origin. If sigma is really large, that says, I don't know anything. If sigma is infinity, basically it says I know nothing. weights, I don't mind if the weights go all the way to infinity. It's all, essentially sigma is infinity makes this maximum likelihood. Or essentially equivalent to that. Any questions? Any other questions?
Would you still call this a regularizer?
It becomes a regularizer. It's exactly that. In fact, this is the probabilistic interpretation of the squared norm regularizer. It's exactly that. Since you've already gone ahead, let me also do that. We want to learn by maximizing the sum of these things, so let me just replace the summation. I'm going to put the max here, and the constants disappear because the constants are independent of W. I'm going to maximize with respect to W. The constants go away when you take gradients, so we don't need to worry about them. Do you have a question?
Yeah, and all these maxes, that's our max, right?
Yeah, yes. Yeah. I use max and argmax interchangeably because if you get the max, you can always track which W got you the max. So I tend to use them somewhat interchangeably. Okay, so the goal of learning a logistic regression classifier under the map criterion is equivalent to solving this optimization problem. So let's clear this slide out and take only the optimization problem. So let's look at this problem. I want to maximize the sum of some term. The sum consists of one entry per training example plus or minus another term that does not depend on the data at all. It's just the norm of the weight vector because it was the sum of, this is exactly the definition of norm. So it is W transpose W divided by sigma square. Sigma square was present everywhere, so I just took it out. This quantity here, this is exactly the same as if I get rid of all the negatives. This is the same as min over W, the sum over I, log 1 plus exponent of minus yi, W transpose I, plus. So I just remove the negatives and I have this minimization problem of two terms. And again, this, so maximizing is the same as minimizing, so I get this whole thing here. So learning a logistic regression classifier under the map criterion is equivalent to solving this minimization problem. And this must look awfully familiar. If for no reason, at least because it's in the homework. But more importantly, this is so similar to the SVM objective that we saw. It's similar in form. There is a summation of some quantity over the data set plus a norm over the weight vector. We've seen this before, and in fact the first question for the homework says write down the stochastic gradient descent algorithm for this. There are other ways of solving this optimization. You might encounter another algorithm if you are reading papers called LBFGS. Let's see if I can remember the name. Limited Memory Broyden Fletcher Goldfarb Sham. The name is the easiest part of that algorithm. It becomes a pain to implement it. SGD is much easier, but LBFGS has interesting guarantees also. So you might run into that. But the point is, it's an optimization problem. We have made it somebody else's problem. In your case, in this case, in the homework, it's your problem. So this is essentially a way of solving for this optimization problem. Solving for this optimization problem gives us a maximum posteriori classifier under the logistic model with the assumption of Gaussian primes. Question?
So for the stochastic gradient descent for the intercept, do you also add the norm or the...
Absolutely. It behaves exactly as what we did for... so what is stochastic gradient descent? The way to think about it is at every step you take one example pretend that that example is your entire data set, write down the loss function. So this summation is the sum over one example. So the loss, the whole objective is the sum of these two things. So you write down both of them and then you take the gradient. So the regularizer still shows up. So I said regularizer, and that's what it is. We assumed that the weights are coming from a uniform, from a prior distribution that's Gaussian, independent of each other, and you take the log of that and you get a square norm regularizer, which we saw earlier for SPMs.
And that's a convex function.
It's a convex function.
Differentiable.
It's differentiable, it's convex. Yes, it has all those good properties. And in fact, if you feel particularly excited about this stuff, try to prove it's convex. It's not terribly hard. The way to do that is to notice that log is an increasing function, exponentiation is an increasing function, W transpose X is convex. Alright, so I want to step up a bit, go back to loss minimization, unless there are questions about logistic regression specifically. If there aren't, I'm going to go back to loss minimization, and these are slides that you hopefully have seen before, but I want to revisit them, given what you've seen now. I can frame learning as loss minimization. We have examples drawn from an unknown distribution. There is a hidden classifier that we would like to find, but we don't know what it is. In the ideal situation, we can define some notion of loss. Think of loss as a penalty for bad hypotheses. And the goal of learning is to find a function that has the minimum loss in expectation over the true distribution of examples. But the true distribution is unknown. So instead what we don't have the true distribution, but we have a sample from the true distribution, and that's called the training set. And instead of minimizing the loss, instead of minimizing the expected loss, we're going to minimize the empirical loss. The empirical loss is simply the average value of the loss over the entire training set. So we are going to try to find a hypothesis that minimizes the empirical loss. This is a template that shows up in multiple ways. Now, what we would like is to find the minimize the empirical loss, but there's a problem here. What if you perfectly minimize the empirical loss? What could go wrong? You might end up overfitting. A classifier that has zero empirical loss is the following. It's called a table or a database. You put all your training examples in the table, in the database. At prediction time, you look at the example, see if it's in the training set. If it is, you give the training label. Otherwise, you toss a coin. It will have zero error on the training set. But it clearly is overfitting. So, how do we handle overfitting? How do we kind of smooth out hypotheses? What's that other term? What is the term in the objective that penalizes overfitting? The regularizing. So we can combat overfitting by using a regularizer, which is a term that penalizes complexity. The loss is a term that penalizes mistakes. The regularizer is a term that penalizes complexity. So instead of minimizing just the empirical loss, we will minimize the regularized empirical loss. And that's what we get. So we have the goal of regularized loss minimization is to find the hypothesis that has the lowest sum of the regularizer plus empirical loss, but there's a trade-off parameter now which tells us how much we like overfitting. With linear classifiers, the most popular kind of regularizer is the square norm. It turns out the square norm regularizer has multiple interpretations. One interpretation is that it pushes for larger margins. This was the interpretation that we saw when we came to it through SVX. Another interpretation is that your weight vector, W, is composed of individual weights. Each weight in the weight vector is drawn randomly from a Gaussian distribution. And we are minimizing or we are solving the maximum, performing maximum a posteriori estimation. That's what we just saw. The square norm regularizer has two different interpretations. If you are Bayesian, what it really means is that we have a particular prior. If you are not Bayesian, it means you can still use the same regularizer, and now the objective is to maximize the margin. There are two ways to reason about the same thing, and once again, it's one of these satisfying things that you can arrive at using two different lenses. Again, it's a suggestion that something is probably right about this. Yes?
Which one was first? Which is more approach?
I don't know actually. I think the probabilistic interpretation came first. I think. I have never thought about which one came first.
Okay.
So, the loss function is a term that penalizes mistakes. Now the question is, if we didn't have to worry about any computational concerns, what is the loss function that you should be minimizing? What is a mistake? Yes?
It's a 0-1 loss.
It's a 0-1 loss. Every time you make a mistake, you lose 1 point. And the loss could just be the average number of mistakes that you made or the total number of mistakes you made. So the ideal loss function is the 0-1 loss. You penalize mistakes every time you have a. So I've written, currently the way I've written it is the loss is a function of the prediction and the ground truth. I'm going to call it the gold. And I have two labels. If the two labels are the same, the loss is 1. If the two labels are the same, loss is not 1, it's 0. If the two labels are different, then you lose 1 point. And adding up all the losses over the training set gives us the total number of mistakes that you make. Ideally, that's what we should hope to minimize. It turns out, for linear classifiers, you can write mistakes as YW transpose X being less than 0. So I can rewrite the same thing for linear classifiers as you lose 1 point if YW transpose X is less than 0. I said less than equal to 0. Otherwise, you lose 0 points. I say you, really it's the weight vector W that's losing the points here, because the weight vector is the hypothesis. Did you have a question? Okay. So that's what we want to do ideally, but minimizing the 0-1 loss is NP hard. So we need to invent surrogates. There are many surrogates. The hinge loss is essentially saying I want to minimize the 0-1 loss, but I don't know how to solve that problem. Instead, I'm going to approximate it with the hinge. Logistic regression says I want to minimize the 0-1 loss, but it's intractable. I'm going to approximate it with the logistic loss. It turns out I can interpret perceptron also from this framework. I would like to minimize the 0-1 loss, but I'm going to instead minimize the perceptron loss. And there is a way in which even the adder boost can be seen as minimizing loss, which is actually the exponential loss. If you like pictures, these are all the losses overlaid on top of each other. On the x-axis or on the horizontal axis is YW transpose X. Here it's loss. On the vertical axis it's loss. So the 0-1 loss is the red line here. It says if YW transpose X is greater than 0, the loss is 0. If YW transpose X is less than 0, then you lose 1 point. That's what we would like to minimize. The sum over these curves over the entire training set is what we would like to minimize, but that's not happening. So instead, the hinge loss says if YW transpose X is more than 1, then there is no loss. If it is between 0 and 1, there is no error here. because the 0-1 loss is still 0. And yet the SVM hinge loss says, even if you are within the margin, you're going to pay some penalty. And if you're going away from, if you're on the wrong side of the margin, the penalty keeps getting bigger. That's what the hinge loss is. The perceptron loss is essentially a shifted hinge. Just like, so the hinge loss is this curve here, the perceptron loss is this curve here. The perceptron loss says, if there are no mistakes, there are no updates. If there is a mistake, then you pay a penalty and that leads to an update. Yes,
So is the SVM essentially perceptron with margin?
that's exactly it. Yes. That and a regularizer. That's exactly what it is. That's why actually in your homework, whenever you implemented perceptron, we had the margin perceptron. It was essentially to foreshadow the SVM.
How does this show the regular?
This doesn't show the regularizer. This is only the loss. Yes. Now, the logistic regression classifier, let's see. Add a boost also is approximating the 0-1 loss with this exponential term. I'm not going to interpret that. The logistic loss is another loss function which says even if you're right, you still pay a penalty. You pay a penalty because ideally I would like it to be more right by pushing more probability. So essentially going farther this way means that you're pushing more probability into the ground truth, towards the ground truth. You're making the posterior look more and more peaked. So if you are here, this essentially says there is still a small probability that the label is incorrect. So I want to make that probability even smaller by going further. That's what the logistic regression classifier says. And these curves all look so different except the 0-1 loss. Actually all of them look different. But actually what happens is if you zoom out this curve, this picture, and I don't have that so I'm going to try to draw it. If you zoom out, what happens is the 0-1 loss still looks like this. But for all practical purposes, all the others look something like this. Except the exponential, which really shoots up. So most loss functions look roughly like this. This side is bad, so you add a penalty. This side is good, so the penalty is either 0 or very low. Yes.
How hard is it to solve the 0-1 loss if instead of being constant, it increases as you go back, but it still goes straight to 1? Because you imagine if the blue line held it up.
This way?
Yeah.
That's the hinge.
Well, except it's a 0 between 0 and 1 on the right hand side.
So that's what the perceptron loss is. It's a 0 all the way here, and
Yeah, what I'm saying is you jump straight up to 1 though.
oh, I see. But that becomes discontinuous.
Okay.
I have to think about it. It's doable. It could lead to weird effects in this region. But I think we can always write an optimization problem. It's not convex. Because, yeah, it's not convex. The other thing to keep in mind is all these 4 loss functions are essentially convex surrogates for the 0-1 loss. The 0-1 loss itself is not convex. Okay. So, seen from this perspective, the logistic regression classifier has multiple interpretations. It's a classifier that predicts probability that the label is 1. It's a discriminative counterpart of the naive-based classifier. It's a discriminative classifier that can be trained using maximum likelihood or maximum a posteriori estimation. And it is exactly the same thing to say that the logistic regression classifier is a linear classifier that can be trained by minimizing the regularized or not logistic loss over the training set. So, in some sense, one of the reasons why the logistic regression classifier is coming at the end of the semester is because it integrates all these different perspectives. I can interpret it as a probabilistic classifier. It's also a linear classifier. It is, just like the SVM, also a discriminative classifier. It can be thought of as a classifier that's trained by minimizing loss. I think, any questions about this? If there are no questions, I'm going to jump right ahead into neural networks, unless there are any pressing issues with logistic regression.
The second part, discriminative counterpart of the naive-based classifier. Can you repeat that idea?
So, the logistic regression classifier can be seen as a discriminative. So, the naive-based classifier and logistic regression, for binary classification at least, and we put more broadly, also form a discriminative generative pair. What that means is the naive-based classifier, even though in order to train the naive-based classifier, you are fitting the likelihood and the prior of the label, and then computing the posterior to make a prediction. Whereas so I can look at it this way: in naive base, for training, find the likelihood, I'm just going to call it like, and prior. For prediction, compute label, that's find the label that has a maximum this quantity P of y given x. That's naive base. For logistic regression, for training, find best, let's say W, such that that maximizes log posterior. Find, or let me put it this way: training involves training directly models P of y given x. At prediction, it's basically the same. But the reason that logistic regression and naive Bayes are discriminative generative counterparts is the functional form of the posterior probability in both cases is identical. They are learning the same kind of a posterior function, except logistic regression directly finds the posterior. Naive Bayes computes the posterior by getting the likelihood and the prior and then coming to the posterior. That's why this is a generative classifier, that's a discriminative classifier, but they form a pair. Because they are at prediction time, they are trying to find the same kind of a function, or they're using the same functional forms. Other questions? So what you should be able to do now is you should be able to solve this optimization problem. This one. And that's what your homework asks you to do. In order to solve this, what you need to think about is rework everything that we saw for solving the SVM. When we were trying to optimize the SVM objective, it looked a lot like this, except this had a different function. It had the hinge loss. For SVM, it was max was 0, 1 minus y w transpose x, yi. So now, and think about all the steps that we went through for optimizing the SVM with stochastic gradient descent. For SVM, there was an additional problem in that the max is not differentiable, so we had to do subgradient. Here, log something is still differentiable, so you don't even have to worry about subgradients. What you need to think about is what is the gradient of this function with respect to w. So you should be able to do that. and in fact that's what you are doing for the first question of your homework, and implementing what you solve, the algorithm you derive, in the second part. Any questions? Alright, I'm assuming there are no questions, so I'm going to switch to neural networks.
Just a quick question.
Yes.
When we're doing the gradient, we're doing it of the whole thing though, right? Not just the loss function?
Yes, yes. Which is why I said it looks extremely similar to the SVM.
Okay.
I have a question about that now too.
Okay?
So because it doesn't, you don't have to separate it into two pieces, theoretically we wouldn't have to check, like there wouldn't be a mistake checking step in the algorithm then, right?
There won't. In fact, that's actually right. There won't be that if condition won't show up. You'll make an update always. And that also reflects in the shape of the loss function. There is no region in the loss function when the loss is 0. So you will always make an update. So that a good sanity check here is that you won't have, and if something to make this kind of an update, else make some other kind of an update. That's what we saw in SVM. You should not have that here. That's absolutely right. Okay, so we're now going to look at neural networks. How many people have used neural networks? 3 people, so nobody. Well, on an average, nobody. So I want to start with a big caveat here. I'm going to introduce neural networks. This is going to be a mild scratch on the surface of this really, really big topic. If you're interested, I can recommend books. There's actually a book called Deep Learning. It's available, you can just find it online. And it's rather thorough and complete in its in what they describe. I'm drawing a little bit from there. Another part of this lecture is from another book called Understanding Machine Learning. This was the same book that I pointed to some people when we were looking at the computational learning theory. So there are multiple sources of this lecture, but really the main thing to keep in mind is I'm not going to talk about any of these named neural networks like restricted Boltzmann machine or convolutional neural networks. I'm going to give you an introduction to the broad topic of neural networks with the hope that this will set you up to learn further on your own. So just to take a checkpoint of where we are, we've seen various classifiers. We've seen decision trees, perceptron, boosting, ensembles, SVMs, and naive-based logistic regression. And we've also seen general principles of machine learning. The most important thing that we have to worry about is that we don't overfit a training set. We've looked at what is learning by answering the question mistake bound learning, the mistake bound model under the mistake bound model. We've also tried to answer it under the PAC model and the Bayesian model. Along the way, we came across risk minimization, which seems to pervade a lot of these topics. And there's this question of generalization versus training errors and how we have to worry about the generalization error and not just the training error. And one choice that we have to make before we start anything is to choose a hypothesis space. Because if you choose a particular hypothesis space versus you choose a different one, this choice could give you different classifiers and potentially different decision boundaries. Across a lot of these classifiers that we saw, the one common thing that kept coming up was that we kept looking at linear classifiers. And one of the reasons was they're easy. We tend to get nice convex optimization problems and they're easy. The other thing to keep in mind is we did not do kernels, unfortunately, so that's something that gives us nonlinear models, but we didn't do that this semester. What we did not really resolve at all was how do we get nonlinear classifiers? And another question that we really kind of skipped completely is where do those features come from? I keep telling you that let's assume that we have some features, but where do those features come from? we can think of neural networks as a way of answering both these questions from a hypothesis-based point of view. So the entire lecture on neural networks is going to first talk about what these things are, what is a neural network, and what kinds of functions they express. With any hypothesis space, you have to answer two questions really. Given a function in that hypothesis space, how do you make a prediction? And the second thing is, how do you find the best function in this hypothesis space? So essentially we need to talk about how to predict using a neural network and how do you train with neural networks. And I'll end this section with some discussion of practical concerns. There are way more practical concerns than what I can possibly enumerate here. I'm just going to give you a slice. So let's start with what is a neural network, and I would like to set this up from the perspective that we've looked at other classifiers in this class in terms of a hypothesis, space. So we've seen linear classifiers. A linear classifier takes a set of features, the x's here, and this is a drawing of what a linear classifier does. You have x's, you have 4 features here, and a bias. Each wire, one way of interpreting the wire is any signal that passes through that wire gets multiplied with it. So here you have W1, X1, and here you have B. All of them get added up, so this gives you your dot product. And then we threshold it. If the dot product is more than 0, we say the label is 1. If the dot product is less than 0, we say the label is -1. Prediction is essentially just the sign of the dot product. What I have drawn here is exactly the same. It's a pictorial version of this thing here. So that's how prediction works. And in order to learn these prediction machines, we have seen various algorithms. Perceptron, logistic regression, and all these things. And in general, we try to minimize loss, as we just saw. And the question that we completely ignored is, where do those features come from? One intriguing possibility is, what if those features themselves came from a different classifier? What if each feature was produced by a classifier? Could do that, right? I mean, you can take some inputs, pass them through a classifier, and get a feature. You do this multiple times, you get multiple features, and that's roughly what you're doing with your decision tree homework. All your features themselves come from a classifier. What if your features came from a linear classifier, a different linear classifier? So what I can do is, I have this one-layer neural network. That's what this is called. Let me separate out the prediction part from the features, from the inputs, and let's say the first feature is coming from a classifier. That classifier has its own weights, a different set of weights. It's not these W's, but it has a different set of weights. The second feature comes from a different classifier, and so on. What we get is a two-layer feed-forward neural network. One assumption I have made here, which is not necessarily always the case, it's almost never the case, is the number of features here is the same as the number of inputs. But there was nothing that required me to do that. I could have another 8 such units, right? So this is a two-layer feed-forward network, which has an input layer, which is what we actually observe. We have an output layer, which is what we want to predict, and a hidden layer. The hidden layer, the way to think about the hidden layer is, in this case, the hidden layer computes a good representation that allows the output layer to make a prediction. So the hidden layer is a learned representation of the inputs. So far so good? What's an obvious question that comes up? So now I have these classifiers here. I need good features for these classifiers, right? The hidden layer classifiers are classifiers that need features. So it's not like I've solved the problem, I've just moved the problem away. Okay, so how do I get, before that, what is a single neuron? A single neuron is, in this case, there's a dot product followed by, in this specific case, a threshold. The dot product followed by a threshold, for the purposes of the next 3 minutes, we'll call this a neuron. So in this case, in this picture here, there are 5 neurons. There are 4 in the hidden layer and 1 output. Okay? But the next question that automatically comes up is, where do I get these features? How do I know that these are the good features that we need for the hidden layer? I can basically do the same process again. I can add one more hidden layer here that act as good features for this is the last layer, this is the penultimate layer. I can add one more set of neurons that act as features for the penultimate layer. And then the question comes up, okay, but what are good features for this hidden layer? I can add one more layer. I can keep adding layers, and that's how you get a deep neural network. So far, so good? Yes?
How do you choose the first ones?
How do you choose the first ones? You use cross-validation to decide how deep is good enough. Which is why you get, models today which have 150 layers. Why? Because it seemed to work. It was better than 149, but worse than 151. There are problems with this worldview, and we'll deal with that as we go along, but that's roughly one way of thinking about it. Let's try to formalize this intuition a bit. Formally, a neural network can be seen as a way of approximating functions. It's a way of approximating real valued functions, it's a way of approximating discrete functions or vector valued functions. It's one of the best or the most computationally and statistically effective, efficient supervised classifiers that we know. And it seems like this family of classifiers are especially good at with data that is really hard to interpret because I don't have enough expertise to decide what are good features, and I've transformed that into a learning problem. One of the reasons neural networks are really the rage today is because of this backpropagation algorithm. The backpropagation algorithm is, we'll get to that, but not today for sure, on Thursday. It's become the de facto module inside a learning algorithm, and it essentially allows us to mechanize the process of inventing learning algorithms. What you're doing for your homework for logistic regression is basically what backpropagation does in a symbolic way. And that's why neural networks are particularly useful have been useful for like a wide range of problems, because you don't have to reinvent the learning algorithm every single time.
One question. What's the hypothesis space? Is there a hypothesis space on each layer? Or?
The whole thing is a hypothesis space. The whole thing is a hypothesis. A neural network is a hypothesis. So any discussion of neural networks would be incomplete without mentioning biological neurons. I know nothing about this stuff, so I'll just mention what I learned from Wikipedia. Apparently, the brain contains neurons, and they have axons and dendrites. That's pretty much all I know. This is the first drawing of a brain cell from long back. None of this, it turns out, are directly involved with artificial neural networks. Artificial neural networks are supposedly inspired by biological networks, but there are so many differences that I urge you, please don't take these the stuff that you see in the media about creating a brain too seriously, because it's written by people who don't know either one of these things. So just be aware. The fundamental neuron that we will look at is extremely extremely different from what is a neuron in the biological sense. A neuron in the computational, artificial neuron is not one thing, it's just a class of functions. That's really the way to think about it. So, these are functions that very loosely mimic a biological neuron in the sense that they also collect inputs and produce outputs, like any other function. It collects, an artificial neuron accepts a set of inputs, typically a vector, but we can reformulate these things very easily by saying that the inputs could be a matrix, and the output is usually either a number or a single bit. It's almost always, in most practical applications, it's usually a real number. The way the artificial neuron works is you take an input, a vector, you take the dot product of that input with a set of weights that the neuron maintains. Add a bias that the neuron maintains, so you get W transpose X plus P, and then you apply something called an activation function. An activation function is typically a non-linear step. We've already seen an activation function, the threshold. Thresholding the dot product is a kind of an activation. The output of the neuron is an activated dot product. We've already seen this. We take some inputs, we apply a dot product, we pass it through this threshold, which in this case is the activation. But the threshold is not the only activation out there. There are other activations that are possible. In the literature, we see many activation functions. Sometimes some people also call them transfer functions. They transfer the dot product to the outside. I could say that the activation is simply the identity function. That gives us the linear neuron, which just says the output is W transpose X plus B. We've seen the sign function. The output could be the sign of the dot product. That's called the threshold or the sign activation. The activation could also be the sigmoid function. The output layer output of the logistic regression classifier can be interpreted as in fact, the logistic regression classifier, all of it, can be interpreted as producing taking the dot product and passing it through the sigmoid activation. So that's the sigmoid unit. Particularly popular in the literature over the last, say, 5 to 8 years is this activation that's called the rectified linear unit, which takes the dot product, checks if that dot product is more than 0. If it is more than 0, it just passes it along. If it is less than 0, it just sends 0. So you get max of 0 and the dot product. Here Z is going to be the dot product. Another historically interesting activation function is the tan H. But there are so many more that an exhaustive survey is rather difficult. So formally, you can think of a neural network, and I'll finish with this formal definition. It's a function that converts inputs to outputs, and the function, the neural network, the entire neural network, can be defined as a directed acyclic graph. An acyclic graph is basically a directed acyclic graph is a collection of nodes with edges, and the edges are directed. The nodes in this graph are organized in layers. Every node corresponds to a neuron. The edges carry information from one node to another, and every edge is associated with a weight. And when a number goes from one node to another along an edge, it gets multiplied by the weight. Usually it's drawn in these kinds of pictures. There's an input, and the arrow here that shows the direction of the arrows, and the notation that I will use is every weight. This is I and this is J. In the second layer, this is the weight associated with the edge from I to J. Now, to define this function, it's a function, right? It's a function that in this case, it's a function from 5 inputs to 2 outputs. It's defined using this graph, but it's still a function. The way the function works is I take this input, I pass information along this edge, multiply it, accumulate it here, do the dot product, pass it through an activation function, and then continue. In order to define this function, yes?
Within a single hidden layer, is each node differentiated by an activation function?
Good question. Technically speaking, there is no such requirement, but in practice, almost always that's how it is. They all have the same activations.
Okay.
It's not how it is, how you asked.
Oh.
So usually, but not necessarily, but usually, a single layer has the same activation.
Okay.
But in order to define the neural network, I need to specify what's the layout of this graph, what are the nodes, what are the edges, and I also need to specify what are the activation functions on every node, and I also need to specify what are the weights on these edges. Once I give you these three things, I get a particular neural network, right? So I get a function. A neural network maps to a function. The function is defined by the structure of the graph, the activations on each node, and the weights. Typically, the structure of the graph and the activations are together called the architecture, and more often than not, the architecture of the network is predefined. It's part of the classifier design. You can think of it as you choose the architecture by cross-validation, say. The job of learning is to discover the best weights for a particular architecture. That's what we will. That's what the backpropagation algorithm will give us. So together, the architecture and the weights give us one neural network. And the last thing that I'm going to say is neural networks are really, really old. They have been around for as long as machine learning has been around, even before the field was named, in fact. In 1943, a seminal paper from Makulo and Pitts showed that linear threshold units can classify certain Boolean functions. 1949, Hebb suggested that there is a learning rule called Hebbian learning, which has some biological interpretations. 1950s, Rosenblatt introduced the perceptron, which was a single layer neural network with a threshold activation, and also showed how to learn it. 69, Minsky and Papert kind of threw cold water on this whole agenda, said that you can't learn, the perceptron can't represent some functions, but you can think about it from the geometric point of view. In the 1980s, starting with Fukushima but carried on by Jan LeCun, there was this idea of convolutional neural networks that mimic biological neurons in the visual cortex, and then there is the backpropagation algorithm that became formalized by multiple people. And since really 2003-ish, there's been a lot of work in neural networks because finally we've been able to train, we've got the computation to handle the scale of data and the size of the networks. And that's why we are able to, that's what has led to this kind of an explosion in neural networks. Alright, I'm 2 minutes over time, so I should really stop. We'll continue further on Thursday. Oh, and I have